For all of its incredible power, there was a fundamental flaw, a monster lurking deep inside the transformer architecture. Because every single word has to attend to every other word. The work doesn't double, it quadruples. This is the quadratic crisis. So, how in the world do you get from the Beatles to giant robots to the AI that's changing our world? Today, we're unpacking that exact story. And it all comes down to some incredibly clever memory hacks that completely rewrote the rules of artificial intelligence. There's a very clean line in AI history, before 2017 and after 2017. To understand this AI revolution, we first need to understand the problem researchers were trying to solve. So let's look at the world of artificial intelligence before that breakthrough moment in 2017. Back then, it was like having a tired intern read legal fine print one word at a time. Models processed language sequentially. If a sentence had 100 words, the model had to grind through the first 99 just to understand the last one. These older systems were called recurrent neural networks, or RNNs. And if you compare RNN versus transformer architecture, their biggest weakness becomes obvious. RNNs process text one word at a time, which meant they couldn't take advantage of modern GPU hardware. We had powerful GPUs built to process millions of operations in parallel, and AI was stuck, moving step by step. Then, everything changed. A research paper from Google introduced what we now call the transformer architecture, and it completely reshaped artificial intelligence and modern large language models architecture. The idea was deceptively simple. Instead of processing words sequentially, what if the model could look at the entire sentence at once? All the words, all their relationships, at the same time. Brilliant. But it created a new problem. If you look at every word at once, you lose the order of the sentence. And order matters. The dog bit the man, and the man bit the dog use the exact same words, but the meaning is completely different. So how did they solve that? With a clever engineering shortcut called positional encoding. By layering sine and cosine waves onto each word's data, researchers gave the model a mathematical sense of position. It wasn't reading order the way humans do. It was feeling position mathematically. An elegant and powerful fix inside the transformer architecture. Once the transformer could process everything in parallel, it unlocked its core superpower, the attention mechanism explained in that original paper. Think of attention as a tiny search engine running inside the model. It starts with a query. For any given word, the model asks, what am I trying to understand right now? What context do I need? Then every other word offers a key. Each one signals what kind of information it contains. Finally, the value carries the actual meaning. The model compares the query to all the keys and pulls in the right amount of value from each word. That's how it determines which words matter most. This attention mechanism is what allows the transformer architecture to weigh the importance of every other word when analyzing a single word. That's why in a sentence like, the animal was too tired to cross the road, so it lay down, the model understands that it refers to animal. It isn't reading in a straight line. It's evaluating all relationships at once. And interestingly, this revolution began casually. The paper was titled, Attention is All You Need, a playful nod to the Beatles song, All You Need Is Love. The name Transformer was not the result of a branding strategy. One of the researchers simply thought it sounded cool. Early documents even included images of Optimus Prime. But for all its power, the transformer architecture has scaling limits. There is a deep structural issue that becomes more severe as models grow larger. To manage costs, engineers introduced a method called KV caching, explained as a memory optimization trick. Instead of recalculating everything for each new word, The model stores keys and values in memory. It speeds things up, but consumes a large amount of expensive VRAM. And this only treats the symptom. The real issue is this: every word attends to every other word. That means computation follows a quadratic scaling problem. If you double the length of the text, you don't double the work. You quadruple it. This is often referred to as the quadratic scaling problem in AI, and it's the hidden tax inside the transformer architecture. It limits context size, it increases costs, and it makes scaling large language models extremely expensive. So, how do you solve a problem that becomes dramatically more expensive as it grows? A new generation of AI architectures suggests a counterintuitive answer. The solution is not remembering more, it's learning how to forget better. This brings us to architectures like Mamba AI architecture. Instead of having every word attend to every other word, Mamba compresses information into an internal state. The key concept is selective memory. It determines what information is essential and what can be discarded as noise. By mastering selective forgetting, it breaks the quadratic scaling problem and moves back toward linear scaling. This directly addresses the transformer's scaling limits. This represents a major philosophical shift in artificial intelligence. For years, the goal was to build systems with perfect memory and complete recall. Now the focus is shifting toward efficient compression and intelligent selection to solve the AI memory problem. And this shift is happening at exactly the right time. There is a principle called the Chinchilla rule in AI, which states that for models to improve, they require roughly 20 tokens of training data for every parameter. The challenge is that we are running out of high-quality human-generated text on the internet to train on. That makes building more efficient AI models essential for the future of large language models. It suggests something profound about intelligence itself. Whether biological or artificial, intelligence may not be about perfect recall. It may be about efficient compression and prioritization. And that leaves us with one final question. As we design AI systems that can choose what to discard, we must ask, what is the most important thing for an AI to forget? Because the answer to that question may define the next generation of artificial intelligence.